In this video, I'm going to discuss polar coordinates. This is section 10.3 in your Larson Pre-Cal book. Previously in your math career, when we give you an ordered pair and ask you to graph it, often that ordered pair is in the form of Cartesian coordinates or rectangular coordinates, so you're familiar with x, y. Today we're going to talk about a new coordinate system, polar coordinates. In this polar system we still have an ordered pair, but we no longer care about the horizontal and vertical change from the origin. Now what we care about is, and instead of the origin, we have what we call a pole, and the positive x-axis we now call the polar axis. So polar coordinates. The pole is the same point represented by the origin in Cartesian coordinates. Our ordered pair will be r comma theta. Now I should mention this is not universal across all of mathematics, but in your book your ordered pairs will be r comma theta. R here stands for the distance of the point to the pole, so the point 0, 0. So r you can think about as the radius of the circle, which would go through that point and would be centered at 0, 0. Theta will be the angle, the central angle between the polar axis, the positive x-axis, and the terminal side of the angle, which would intersect with that point. So r comma theta, what we now care about is the distance from the pole, and theta, the rotation, the angle of rotation from the polar axis. Since you realize that we have a right triangle, if you connect this point to the former positive x-axis, what we'll now call the polar axis, then similarly to what we've done several times before, cosine of theta will be adjacent, which was our old x value, the horizontal change from the origin to the base of this point. So cosine of theta would be x over r. When you solve for x, you have that x is equal to r cosine of theta, and y similarly will be r sine of theta. And that's an error I will fix and did not notice. Sorry about that. So x is equal to r cosine of theta and y is equal to r sine of theta. Now because of that, we'll actually have some conversion formulas so that when we need to change from rectangular coordinates to polar coordinates, x is equal to r cosine of theta, y is equal to r sine of theta, r and theta here represented by our polar coordinates. If we need to find r from x and y, then r is equal to the square root of x squared plus y squared using the Pythagorean theorem. So we have this relationship x squared plus y squared equals r squared. You'll notice that's an equation of a circle centered at the origin, which would intersect the point x comma y being the exact same point as r comma theta here, but in rectangular coordinates. To find our angle, we can use the fact that if we are given, for instance, x and y, then tangent of theta is y over x, so of course theta is equal to arctangent of that ratio. So these four conversion formulas, and when I have this arrow here, I really consider that the same formula, and this last one is the same as well, but we can write those in different forms. So these four conversion formulas are used quite frequently in, say, a Calculus 2 or Calculus 3 class when we need to change our variables from rectangular coordinates to polar coordinates. Often polar coordinates are so much useful when we're graphing circular graphs and any equations that have maybe deal with circles or polar functions, and those are often easier in terms of polar coordinates. So this is a new coordinate system that we're going to discuss today. Now Cartesian coordinates, you're familiar with this horizontal and vertical change from the origin. For polar coordinates, the graphs look different. So the graph paper even, you'll notice here we have squares, unit squares. We care about the horizontal and vertical changes, so our movements are strictly right, left, up, or down. In polar coordinates, we care about two things: the distance from the origin, the distance from the pole, and the rotation. So we care about the distance from the pole and the angle measurements. Our graph paper looks like a whole bunch of concentric circles, and so that is, if you ever see graphing that is working in this form, that's usually using polar coordinates. I have graphed these same points over on the right. You'll notice 2, 3 in rectangular coordinates or Cartesian coordinates. On the right hand side, we care about the distance to the pole. So since r squared is equal to x squared plus y squared, 2 squared plus 3 squared, so you'll have 4 plus 9 is 13. This r value would be the square root of 3, and theta would be arctangent of y over x, so 3 over 2. Now, of course, you won't have nice values for everything, so you can see here is my theta measurement, the rotation from the polar axis, but that actual value would be given by this approximation, or this evaluated. Ship radar, that might remind you of polar graphing. So here, because of the shape of a globe, then on ship radar they use so ship radar is very similar to this polar coordinate. So ship radar might remind you of graphing and polar coordinates. Again, we care about the distance from a location and that angle change. You can see the angles denoted on, they are not using the unit circle as we would use it, it's rotated, but they have the angle measurements centered around the edge. When we plot polar coordinates, so again keep in mind r is given and then theta is my second coordinate. When we plot these, we look at the distance from the origin, so you might go out 4 units, that would be the circle with radius 4, and the rotation 15 degrees. Remember that 30 degrees is pi over 6, so half of that would be pi over 12, and I have a here at 4, 15 degrees. To graph negative 360 degrees, maybe pause the video, take a minute and try that yourself. Now I haven't even discussed what to do with negative r values, so let's start with the angle first. 60 degrees will of course be pi over 3. So normally if this were 3, 60 degrees, I would go out to the third circle along pi over 3 or 60 degrees. Because that's a negative 3, I wonder what you think we should do. If your instinct was to go in the opposite direction, you would be completely correct. So along the ray for 60 degrees, instead of going outwards towards 60 degrees, we're going to go in the opposite direction so that we go down to the third quadrant. B would be here in quadrant 3. C, the fifth circle, so 1, 2, 3, 4, 5, 105 degrees, keep in mind that's 90 plus 15, so I've graphed it right here so that it appears in quadrant 2. For pi over 2 would be north, straight north from the pole, but since I have a negative 4, we've gone to the negative y-axis, and there is D. E, I would go along pi if that were positive 6, but since it's negative, we go in the opposite direction. F, 225 degrees, so we're in the third quadrant, and we go out to the fifth concentric circle so that F is down here in the third quadrant. Now here, if we were in class, I would pause and ask you some questions. Like E, isn't there an easier name for E, like maybe 6, 0, which would be the same point you're familiar with in rectangular coordinates? And you'd totally be correct. So the question that you're asking, you might be asking yourself is, well, are each of these ordered pairs unique? And the answer would be no. There are multiple representations for the exact same point. Well, we'll discuss that. For the point 3, 5 pi over 3, I have it denoted down here. 5 pi over 3 would of course be in quadrant 4, and I would go out to the third concentric circle. And that point may be off a bit. That was difficult on PowerPoint, but you're here in quadrant 4. There are many representations, infinitely many different representations for the same ordered pair. So keep that in mind. They are not unique for polar coordinates. We could have a negative angle, so negative pi over 3, and I could use positive 3 for the r value there. For 2 pi over 3, because that's in the opposite direction, I could use a negative r value, and so I could have negative 3, 2 pi over 3. Negative 4 pi over 3 would, since negative 4 pi over 3 is coterminal with 2 pi over 3, I could have a negative r value there as well. each of these, so there are 4 different examples here, and they are not the only representations. Each of these represent the exact same pair, ordered pair, however. So keep in mind there are multiple representations for the same point. Notice that r and theta could be negative, r could be negative, r could be positive, and theta negative, etc. Do notice, and the book will talk about some formulas. I don't like to get you overwhelmed with the formulas, but just some patterns here. If r is positive, then the thetas will differ by pi, and that makes sense because if your r became negative, you'll go in the opposite direction, so pi units away. So you'll notice here when r became negative, 5 pi over 3 minus 3 pi over 3 gives me 2 pi over 3. You'll notice that as long as r is negative here, these will differ, so 2 pi over 3 minus 6 pi over 3 would give you negative 4 pi over 3. They will differ by 2 pi since they are coterminal. Similarly with 5 pi over 3 and negative pi over 3, they are coterminal. So to you guys, you'd probably think, well, that's the same angle, and it's coterminal is what that means. So the r value didn't change with those, but the angles are coterminal. If you do change from a positive to a negative r value, your angle will change by pi units because you are going in the opposite direction. Again, don't get too worried about that, but just recognize that there are multiple representations. To convert to rectangular coordinates, this would mean that your formula or your point was given to you in polar coordinates. So maybe 4 comma 5 pi over 4, it's understood that r would be 4 and theta would be 5 pi over 4. Using our equations from earlier, x is equal to r cosine of theta, plugging in 4 and 5 pi over 4. Since 5 pi over 4 cosine of 5 pi over 4 is negative 2 square roots of 2, and you're multiplying by 4, so this should be negative square roots of 2, negative 2 square roots of 2. And then sine, because that is also negative, so sine of 5 pi over 4 should have been negative 2 square roots of 2. Then we get negative 2 square root of 2, comma, negative 2 square roots of 2. Notice that this point and this point, if you graph them, then you want to make sure that they land in the same place. Both of those will land in the third quadrant. For the second example that I have, 5 comma negative 2 pi over 3. So plugging those into this formula, cosine of negative 2 pi over 3, cosine of negative 2 pi over 3 is negative, so that should be negative 1/2 times 5 is negative 5/2. Sine of negative 2 pi over 3 is negative root 3 over 2. Multiply it by 5, I have that this is the ordered pair representing the second point. So go ahead and pause the video and make sure that both of those examples make sense. Remember that when you graph it in polar coordinates, it should land in the exact same place as where it would if you were graphing the Cartesian ordered pair in the Cartesian plane. And so that's be mindful of that, and it's very helpful to check your work, to go back through to make sure that you have that answer correct. You'll notice I made an error there, so that wasn't quite making sense when I first looked at it. X is equal to r cosine of theta. This should be 3 cosine of 45, which gives me 3 root 2 over 2. This would be my ordered pair for 3 comma 45 degrees. Again, if I graph this is in quadrant 1, and this would also be in quadrant 1. To convert to polar coordinates, this would mean that you may be given rectangular coordinates, and you now need to find polar coordinates r comma theta. We will use the last two conversion equations that I had on the slide previously. If your ordered pair x is equal to negative 5, y is equal to negative 5, you will plug that in for r, and you will plug that in for x and y and solve for r and theta. Now, keep in mind that arctangent is only defined for 2 quadrants. If this is a point that is in quadrant 2 or 3, you must add or subtract pi depending on which quadrant you need to be in. So for instance, when I plug in negative 5 and negative 5, I'll have arctangent of 1. Theta will certainly be pi over 4, but you'll notice negative 5 will not match up with pi over 4. It's in the third quadrant. Yes, you need to add pi to that value. So pi over 4 plus pi is 5 pi over 4. So let me show you what I mean by that. If I plug 5 in for x and y, I'll have the square root of 50. That simplifies to 5 root 2. Arctangent of 1 would of course be pi over 4, but because we're in quadrant 3, we need to add pi to that, and we have 5 pi over 4. If you graph this in rectangular coordinates and you graph this in polar coordinates, they will lie in the same quadrant. For 0, 6, plug in 0 and 6, I'll have that r is equal to 6. Arctangent of 6 over 0 does not exist. That tells me I'm either at pi over 2 or 3 pi over 2. Graphing this lets me know I'm at pi over 2. So what I'm trying to get at, if you graph these often, you don't even need to use the conversion equations, because using the graph in rectangular coordinates is often enough information, gives you enough information to find the polar coordinates intuitively, or just using a bit of common sense there. Now for something like -3, 4, that isn't going to be one of our special angles, so you would need to use these formulas. R is equal to, so you'll have the square root of 9 plus 16, which of course that's a Pythagorean triple, 3, 4, 5. So I'll have the R is equal to 5. Theta is equal to arctangent of -4 over 3, because that will give me a value that is in quadrant 4, and this point is in quadrant 2. I have added pi so that I get approximately 2.214 radians. My ordered pair leaves me with this. Equations. If you were given an equation in rectangular form, such as a circle, you'll notice this is the circle which has center 4, 0 in a rectangular plane with radius 4. By plugging in the conversion formulas, x equals r cosine of theta and y equals r sine of theta, I can expand this so that I have r squared cosine squared minus 8r cosine. This is a binomial, so I have expanded that part, and then my r squared sine squared is written here. R squared cosine squared plus r squared sine squared is simply r squared. So, and I've subtracted 16 from both sides so that I have an equation that looks something like this. Now, typically I ask you to factor. So what I would ask you here to do is possibly factor out on the left an r. Now because that will give you the product of two equations equals 0, r could not equal 0 here because that only gives you the pole, a single point. So the equation that we end up with is r minus 8 cosine of theta equals 0, which is the same as saying r equals 8 cosine of theta. This is the equation for a circle with center 4, 0 and radius 4. You'll notice that the diameter here, so the radius times 2 is 8. 8 cosine of theta, this number out front is giving you the diameter of the circle. This equation and both of these equations represent the exact same circle. It's simply that this one is written in rectangular form and this one is written in polar form. I want to talk to you about circles. This is the graph of that last circle, x minus 4 quantity squared plus y squared equals 16. It's the same equation as the polar equation, r equals 8. It's the same graph as r equals 8 cosine of theta. This is in polar form, however. Circles in polar coordinates, if you have a circle centered to the pole, it will always have this form, r equals 8 cosine of theta or r equals 8. This is actually not of either of those forms, but what I've done here, this is the graph of r equals cosine of theta plus sine of theta, so I've added a term for cosine and a term for sine, and you'll notice that's where we get shifting so that we are not centered around one of the axes. Limaisons, a French word, it's similar to escargot. So the Masons, they have the form r equals a plus or minus b sine. So a and b are constants here. Again, if you have sine, your graph will have symmetry around the old y-axis. These first two that I have graphed have sine in them. The last two that I have graphed have cosine because of the symmetry around the old x-axis. If a is less than b, so you'll notice 1 here is a, 3 is b, so a is less than b, then my graph will have an inner loop. So a limaison of this where the ratio of a or b are less than 1 will have an inner loop. Here is my equation. You'll notice you have a negative here. When you have a negative, it will be on the lower half of the plane. A negative and a negative. A positive would have flipped it so that it would have been on the positive part of the plane. Now this second one is a cute one for nerdy valentines, if you ever need to make a nerdy valentine, a cardioid is a lemmaison where A is equivalent to B. Here I have the graph of 2 minus 2 sine of theta, a classic cardioid. You'll notice it has that nice heart shape. Lemmaison with a dimple would exist with this ratio, and you can see the one that I have pictured here and compare those constants. And if that ratio gets larger than 2, then that dimple we sand out that dimple so that we get kind of a smoother figure. Now it's not a circle, but it's kind of like, it reminds me of a circle that you dropped and kind of flattened a little bit on one side. So these are the 4 cases of the lemmaison. And here I have rose curves. So rose curves have these 2 forms. Again, sine has symmetry with respect to the y-axis always, and cosine has symmetry with respect to the x-axis. If n is even, so you'll notice in this picture right here, you'll have twice as many petals as n. So this graph was created with a 2 theta. The graph on the right had a 3n. So if n is odd, you'll have exactly that many petals. I encourage you to play around with this and try new graphs on your own. A limnoscate it looks like an infinity symbol. These are harder to graph on your calculator. You can't graph these on your calculator without using square roots, because these have the form r squared equals a constant squared sine of 2 theta. The length of the petal will be a, and cosine of 2 theta, you always have the form sine or cosine of 2 theta for a limnoscate. They look like an infinity symbol, and this one, it looks kind of like a tilted infinity symbol using a sine function. There are many variations on these graphs, so I encourage you to have some fun and play around with these. This would be 4 sine of 3 theta, so you can see the 3 is what gives it 3 petals. 4 affects the length of the petal, but when I add 2, that would be a translation on it, and so you can see that now adding 2 makes these inner loops as well. 1 over theta, so while this wouldn't be one that we would necessarily discuss as frequently in mathematics to find something like area, this is a fun graph to play around with. So 1 over theta, you can think about it as theta gets larger, r is taking the reciprocal of those values. R equals theta. As theta grows, then r is wrapping around along with it. So you have that constant growth there. So r and theta are both growing linearly in polar coordinates. So just to remind you, you can graph these on your calculator, and I encourage you to have fun. You can also graph these on Desmos. So if you graph and go to the graphing calculator in Desmos and press the tool icon, when you change the grid system to polar coordinates, then you'll be able to see those. Now, it doesn't work well with polar coordinates, I'll be honest, but polar graphs, it works wonderfully. So 3 cosine of 4 theta, you'll notice that this has 8 petals, 1, 2, 3, 4, 5, 6, 7, 8. The length of each petal is 3 units long because of my A value. And so I'm going to put this on Google Classroom, but I'm not going to require that you do this outside of the assignment that I made, because I'm not sure that we all have printers. But in a regular trig class, I would have had you do these. We would have done this. I would have done this up on the board. So I tried to do this in different colors. Here you'll notice that I have a graph. I would have talked a little bit about symmetry. I'm gonna skip over that right now. If you remember from algebra, I talked about even functions, odd functions, and origin symmetry. So this is related to that. Polar axis is kind of like even symmetry. So when you plug in negative theta and the negative cancels out, if you have that and you get the exact same function, which we don't here, then we have polar axis symmetry. It's similar to even. This is an idea that you will use later when you are integrating. So what we were doing right here is integrating to find the area of this half circle. If we did that in rectangular coordinates with x's and y's, that's a very difficult problem. Changing it to polar coordinates, it becomes a piece of cake. Thank you guys for your attention. I wish you the best of luck.